This video will review factoring quadratic expressions. We'll start by reviewing algebra tiles. We'll factor some quadratic expressions with algebra tiles, connect that process to using an area model, look at the diagonals of an area model, and then do a couple examples. So these are your 6 basic algebra tiles. They're named after their area. So if we look at that x squared tile, it is x squared square units because that's the area. And we know that the height has to be x and the base has to be x in order for it to have an area of x squared. Below it we've got the x tile, which is x square units of area because its dimensions are x units by 1 unit. The unit tile has dimensions 1 by 1. We've got an xy tile up here that has dimensions x and y. The y tile is y by 1, and the y squared is y by y. The lengths labeled x and y can't be measured by our unit tiles, even if we could match them up physically, because they're meant to represent unknown quantities. So if I wanted to make the expression or the term 4x, I would need to have 4 x tiles. I could make a more complex expression, 5x plus 3y plus 2x squared plus 1. I'd need 5 x tiles, 3 y tiles, 2 x squared tiles, and a single unit. We can look at one more example, 4y plus 2xy plus y squared plus 5. I need 4 y tiles, 2 xy tiles, a single y squared, and 5 units. So the coefficient on each of those terms is telling me how many of each tile I have. To factor one of these quadratic expressions means to rewrite it as a product. So if I'm factoring x squared plus 5x plus 6, I have to start with that many tiles. And what I'm going to do is try to rearrange those tiles in a rectangle so that I can rewrite the area as base times height. So I'm going to start lining up the lengths that are the same size, because I know those will fit together. And it looks like I need to rotate some of my tiles so that they match up, and that's okay. When I put 2 x tiles on each side of the x squared, it looks like I've made space for 4 unit tiles in that top corner. And so it doesn't matter whether I put that last x tile on the top or on the side, because either way I'm going to make space for 2 more units. So when I have my final rectangle, I can see that the dimensions are x plus 2 times x plus 3. And I can rewrite that original expression to say just that, x plus 2 times x plus 3. So we've factored a quadratic. Before moving on, we can connect this to using an area model. And when we use an area model, I don't know how much space everything is going to take up, so I'm just going to draw a rectangle. And I'm not going to draw it to scale because I don't know how long everything will end up being. I'm going to start by putting the x squared tile in the bottom left corner, and you can see on my algebra tile diagram that if I make that choice, the x tiles have to go above and to the right, which leaves space for the 6 unit tiles diagonally across from the x squared tile. I know that my 2 empty spaces need to add to 5x, because that's how many x tiles I have to use. And I want to multiply to the product of the diagonal that we do know. So 6 times x squared is 6x squared. I'll be showing you why that's true in the next slide. So if I think about the multiples of 6, I've got 1 times 6 and 2 times 3. And I know that I'm adding and multiplying to positive terms, so both of my terms that I'm choosing need to be positive. So that means I'm going to use 2x and 3x. Once I've got the inside of my area model filled out, I can pick a column or a row I usually start with the bottom row, but it doesn't really matter where you start. And I want to pick out the greatest common factor. So x squared and 3x both share the factor of x. If I have a height of x there, I need a base of x in order to get my area of x squared. And so if I've got this base as x, the height here that will give me an area of 2x is 2. And if I've got a height of 2 here, the base here that I need to give me an area of 6 is 3. And I can double check that this height of x, which is also here, times the base of 3 does give me 3x. And so I see that my area model as a sum is x squared plus 5x plus 6, and as a product is x plus 2 times x plus 3. So I've got an area model set up here that is just variables. So its base is a plus b, and its height is c plus d. So it's representing the product of a plus b times c plus d. If I fill it in, a base of a and a height of c gives me an area of ac. A height of c and a base of b gives me an area of cb. A height of d and a base of a gives me an area of dA. And a height of d and a base of b gives me an area of dB. When I look at the diagonals, so here's one diagonal and here's the other, what I want to do is take both of the terms in the diagonal and multiply them together. So a times c times dB is the same as a times b times c times d, because I just reordered the multiplication. And the other diagonal, I've got dA times cB, which I could reorder to be a, b, c, d as well. So we see that in an area model, the diagonals always multiply to be the same expression. So now we're going to do a couple examples. If we're trying to factor x squared minus x minus 12, I'm going to start by drawing my area model. I'm going to decide to put the x squared tile in one of the spaces. I usually do the bottom left, but it really doesn't matter. And then the unit term, which is negative in this case, needs to go diagonally across from it, because of the way when we use algebra tiles, all of those pieces fit together. So I'm looking at my empty diagonal, and I want it to add to my x term, which is negative 1x, and I want it to multiply to the diagonal that we do know. So negative 12 times x squared is negative 12x squared. Thinking about the numbers that multiply to 12, I get 1 times 12, 2 times 6, and 3 times 4. Now I know that I'm multiplying to a negative number, so either the first number in the pair could be negative, or the second number. So I could have 1 times negative 12, 2 times negative 6, and 3 times negative 4. And I want to add to negative x, so the pair that I'm going to use is 3 and negative 4. So it doesn't matter which empty spot you put those in. And once you've got that, we're going to start by picking out the greatest common factor of a single row or column. So let's mix it up, and I'll start with this left column. The greatest common factor of 3x and x squared is x. So if I've got a base of x, the height I need to get an area of x squared is x. If I've got a height of x, the base I need to get an area of negative 4x is negative 4. If I've got a base of negative 4, the height I need to get an area of negative 12 is negative 3. And, oops, it looks like I just messed up here. So negative 4 times negative 3 would give me positive 12, but I really want negative 12. So I just want positive 3 here. And I noticed that because I was checking that a height of 3 and a base of x gives me 3x, which at first it didn't. So I can rewrite my sum as the product of x plus 3 times x minus 4. Alright, let's look at another example. 2x squared minus 9x minus 5, so I'm going to start by drawing my area model. By the way, you should feel free to pause the video and try this for yourself, and then make sure that I'm doing it the same way. So I filled in my x squared in my units term. I'm going to add to negative 9x. I'm going to multiply to negative 10x squared. The factor pairs of 10 are 1 times 10 and 2 times 5. I'm multiplying to a negative, so either the first number in the pair or the second one could be negative. And adding to negative 9x means that I have to use positive 1 and negative 10. So that's positive 1x and negative 10x, because I'm adding to negative 9x. And then I'm going to start to get my my dimensions on the outside. So I'll start with a different one again. The greatest common factor of negative 5 and negative 10x is negative 5. If I have a base of negative 5, I need a height of positive 1 to get an area of negative 5. If I have a height of 1, I need a base of x to get an area of x. If I have a base of x, I need a height of 2x to get an area of 2x squared. And I can double check that my height of 2x and my base of negative 5 give me an area of negative 10x, which they do. And so I can rewrite my sum as a product of 2x plus 1 times x minus 5. Got one more example for you. 6x squared plus 7x minus 20. So I'm adding to 7x, multiplying to 6x squared times negative 20, which is negative 120x squared. So this one's going to have more factor pairs than usual, or more than the last two examples we looked at. So I've got 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 24, 6 times 20, 7 doesn't go into it, 8 times 15, and 8 times 15 looks like the pair I'm looking for. So thinking about one of those numbers in the pair being negative, I'm going to choose 8 and 15. And because I'm adding to positive 7x, I'm going to make the larger number positive. So positive 15x and negative 8x. So starting at a single row or column, my greatest common factor there is 5, a height of 5, and a base of 3x give me an area of 15x. A base of 3x and a height of 2x give me an area of 6x squared. A height of 2x and a base of negative 4 give me an area of negative 8x. And just checking, negative 4 times positive 5 does give me negative 20. So that's that area there. And I can rewrite my area as the product of 2x plus 5 times 3x minus 4. Alright, so be sure to check the extra practice sheet if you need help building this skill.